Okay guys, and so if you missed class, I want to give you the video on the quantum mechanical model and electrons. It can be kind of complicated, but I'm going to try and just make it as simple as possible. I might have to make a couple of these to get through the material. So anyway, a lot of the foundation laid today is just that. It's foundation. It's facts that you need to know. And we'll get into some of the explanations as we go. So anyway, quantum mechanical model is what we're looking at, and the first thing I want to do is I want to give you a definition of an atomic orbital. So write this down. Atomic orbital is a 3D region of space around the nucleus where electrons are likely to be found. It deals with probabilities. I'm just going to go, if you need to pause to write stuff down, then pause it. I'm just going to go for time's sake. Remember, the Schrodinger equation is the math equation that Erwin Schrodinger gave us that describes electrons as waves, and it deals with probabilities. It doesn't deal with certainties, it deals with the probabilities. Where are electrons likely to be found? So for example, probabilities are like this. During class time at school, where are students probably going to be? Well, they're probably going to be in the classroom. During passing period, where are students probably going to be? Well, they're probably going to be in the hallways. Doesn't mean they have to be in the hallways or they have to be in the classroom, but that's where they're likely to be. That's what the Schrodinger equation gives us. It gives us probabilities. A very important thing is that atomic orbitals, this definition I just gave you, can hold 2 electrons at most. It cannot hold more than 2 electrons, which that gives rise to questions if you're a thinker. So for example, if you have an atom with 35 electrons, but orbitals can only hold 2 electrons, that must mean there are many, many orbitals in the atom, which is true. Note, just a side note, that it's an orbital. It's not an orbit. The electrons don't orbit the nucleus. That's a misnomer. It's an orbital. It's a region of space. It's a volume that electrons are likely to be somewhere in that volume. We don't care exactly where in that volume. They're just somewhere in that region of space. They don't have to be orbiting the nucleus. And so those are some definitions. I want to kind of tie this a little bit so what you learn in some of the younger grades. And so for example, in younger grades, you probably learned that, or you probably had a problem like this. Hey, here's a nucleus. Here are these, ooh, that's not a very good circle. Here are the energy levels around an atom. And if you have, say, an atom that's got 11 electrons, where would you put those electrons? And you probably learned, you may or may not remember, most of you probably should remember this though, that hey, I can put 2 electrons on the first ring, and I can put 8 electrons on the second ring, and that would give me 10 electrons. I'm going to put 1 electron on the third ring. You probably did a problem like that, and you probably remember a problem like that. What we're doing is we're going to take basically this little idea that you learned, and we're going to go into vast detail about it, about where exactly these electrons are, because it's not this simple, and this model is not even correct, although it's a very good visual aid to help us understand. And so I'll refer to this model. Just realize that, hey, electrons don't orbit these rings. That's just not what's happening. The rings help represent energy levels, which is, there's a principle behind it that's true, but the model is not necessarily correct. And so we'll refer back to this a little bit. First, to get us going though, I want to give you 4 quantum numbers. These are very simplistic viewpoints of our quantum numbers, but it's important. These describe electrons. That's what quantum numbers do. They describe electrons as far as in conjunction with Schrodinger's equation. So the 4 quantum numbers are these. The first one is the principal quantum number. I'm just going to put Qn for quantum number. And what this is describing is it is describing the energy level that the electron is in. That's what it tells you, the energy level. There are 7 energy levels that we're going to be looking at. There can be more than that, but generally it's 7 is what normal unexcited atoms have. The second quantum number is actually called the angular momentum number. That doesn't really mean a lot to you. It's not going to mean a lot to you. We're not going to talk about it a whole lot. As far as the practicality, what that means for you, the angular momentum quantum number, is it's talking about the energy sublevel. Oops, not energy level, energy sublevel. Which for us is going to be defined by the shape of the sublevel. The third quantum number is the magnetic quantum number. The magnetic quantum number, and that for us is going to be the three-dimensional orientation of the sublevel, effectively, is what we're doing. So how is that shape oriented in 3D space? And the fourth quantum number is the spin quantum number, which is the, we'll just say the electron spin or rotation, not revolution. How is the electron spinning on its axis, like the Earth spins on its axis? The Earth also rotates the sun. We're talking about the spin. Does it spin clockwise on its axis like a top where you spin it one way, or do you spin the top the other direction? How is it spinning? So those are the four quantum numbers. With these numbers, you can describe electrons and atoms in great detail. And so we're going to base what we're learning off of these quantum numbers. So we need to get some facts out there. So I'm just kind of throwing some pieces out there right now, and then we'll put the pieces together. Throwing all the puzzle pieces on the table before we start organizing the pieces into a picture. And so we're going to make two tables. These two tables are very, very important. You need to basically memorize the information in these tables. How you memorize it and what order you memorize it doesn't matter to me. Just know the information. And so we're going to have a table that has energy levels, number of sublevels, and sublevel types. And we'll fill in that data. And so the first energy level, so that first ring around the atom that you learned in 8th grade, if you will, and how many sublevels it has one sublevel, and that sublevel type is an S-type sublevel. S is just a label, it's just a name that we give it. It doesn't have any real meaning behind it. We could have called it X or Y or Z or whatever. It's called S. Okay. The second energy level has two sublevel types. It has an S sublevel and a P sublevel. Now, obviously, these two S sublevels will be similar to each other. They will be different, but they will be similar. And we'll get into that in a little bit. The third energy level has three sublevel types, S, P, and D. The fourth, fifth, sixth, and seventh energy levels have four sublevel types. They have S, P, D, and F sublevels. And so, again, all these S's will have some similarities because they're all S's. Now, they'll be different because they're on different energy levels. All these P's will have similarities because they're all P's. They'll be different because they're on different energy levels. S and P are different. P and D are different, etc., etc. All right, next table. So if you need to pause, but I'm moving on for time's sake. Next table, we will have another table, sublevel types, shapes, orbitals, and maximum of electrons. So our types from the previous table, we have S types, P types, D types, and F types. Now, the equation, the Schrodinger equation, gives us these graphs. So when we plug in data, we get these graphs out, and that's where these shapes come from. They don't just come from thin air, they come from the equation. So the shape of an S is a sphere. That is that three-dimensional region of space around the nucleus where electrons are. So these shapes are, that's what these regions are. They're these based on these shapes. There's one orbital for S sublevels. Now again, the orbital shape is a sphere, and orbitals can hold two electrons. And so with one orbital, we can hold two electrons on the S-type sublevel. Now, P-type sublevels are dumbbell shaped, is how we could call those. They're dumbbell shaped. There are three orbitals for those. So 3 orbitals times 2 electrons per orbital would give us a maximum number of 6 electrons possible in a P sublevel. D sublevels are 4-leaf clover shaped. The math gives us 5 possible solutions for that, the Schrodinger equation. 5 orbitals, each orbital containing 2 electrons, we could put up to 10 electrons in a d sublevel. F sublevels, or we'll just say they're complex. There are 7 solutions to the equation, giving us 14 possible electrons in an F sublevel type. All right, and so let's kind of put some pieces together as far as that goes. Here's what we got. In your little 8th grade science class, or 7th grade, whatever class it was, you got these little rings. These rings represent the energy levels, which is fine. That's a good representation. The closer to the nucleus, the lower the energy. The higher, the further the energy. So if we have, according to this diagram here, 7 energy levels, then we could have potentially 7 rings around our nucleus. Now, here's the thing. It's not just a ring. It's not just an energy level. There are energy sublevels. So if we took a magnifying glass and zoomed in on that 3rd ring, and this is technically not correct, but I'm just trying to give you a visualization. We zoomed in on that 3rd ring. Well, actually that 3rd ring is 3 rings, because the 3rd energy level has 3 sublevels, and there's an S-type sublevel, a P-type sublevel, and a D-type sublevel in that 3rd energy ring. And so we could even label them. We could say, well, the one closest to the nucleus, that's the 3S sublevel. The next one out, that's the 3P sublevel, and the next one out, that's the 3D sublevel. Now again, I want to emphasize that is not correct as far as there are these rings. The electrons don't move in these rings. But as far as a visual representation of the fact that there are these energy levels and energy sublevels, this works very well as a concrete model for us, if you will. And so we have energy levels and energy sublevels, and then within these energy sublevels, you could zoom in if you would. Again, this is not technically correct. You would have in here orbitals. And if it's a D sublevel, well, D sublevels have 5 orbitals. And so there would be 5 different orbitals inside that D sublevel. And each of those orbitals could hold 2 electrons, so we could have 10 electrons in this D ring, this 3D ring, if you will. Okay? And so that is a lot of the pieces laid out. Now, this also ties into 8th grade, where you were told, hey, I can put 2 electrons on this first ring. I can put 8 electrons on that second ring. Depending on who your teacher was, you were told either 8 here or potentially 18 if they were talking about valence or just in general. And so how does this tie in? Well, let's go look at the first energy level. The first energy level only has S sublevels. The S sublevel has 1 orbital which holds 2 electrons. There's the 2. That's where the 2 comes from. If you look at the second ring, which they told you has 8 electrons, well, go back. The second energy level has S sublevels and P sublevels. Well, S sublevels have 1 orbital. P sublevels have 3 orbitals. That would be 1 plus 3, 4 orbitals times 2 electrons per orbital. There's your 8, or 2 plus 6 gives you 8 electrons. The third energy level, if they told you 8, they stuck with the S and P. If they told you 18, well, they went ahead and they did 3 sublevels, S, P, and D sublevels. S has 2 electrons, P has 6, D has 10. You add those up, you get your 18 electrons. And so what they taught you is a very simplistic viewpoint. It works, it's fine, it gives you some basic data. We're just looking at much more complicated, a much more realistic view of how the electrons are in the atoms. Okay, and so this was a throw all the puzzle pieces out there. All right, I'm gonna come back. I'm gonna make a second video. We're gonna look at some actual computer images of some of the orbitals and just get some ideas of how they work and all work together. Shouldn't be a longer video. It shouldn't be 15 minutes for the second one. So watch this again if you need to, and then I'll get the second one up as well.